Swayam Prabha. Digital India. Educated India.
When oxygen atom is formed in some form, and if it sees H2O, it can form this branch OH and OH. So, everywhere we have O and H2O, it will have OH radicals formation. So, these are called chain branching systems, and this OH will again react with some O atom or some other atom to form another component. So, this branching process keeps on happening, and so in the system of chain branching, it is possible that concentration of radical species can build up, causing rapid formation of products. Although it starts with a chain initiation, and after this branching, when subsequent number of radicals are formed, it accelerates the chemical processes, and some point of time they take the complete hold of the entire reaction mechanism systems, or they have a dominance of overall reaction steps. So, in fact, this is the concept that the chain branching reactions are responsible for a flame being self propagating and are essential ingredient for the combustion chemistry. So, in the combustion viewpoint, if you want to have retain a sustained flame, then we must keep on generating these chain branching systems, and the flame can propagate on its own. Many times what happens, these chain branching systems have serious consequence. Maybe they are basically create an explosive species. For example, when we have hydrogen and oxygen, when they exist in molecule form and they do not oxidize, then there is no question but they are safe. But as long as they start reacting through these branching systems, they can lead to explosive behavior of the mixtures. We will explain this fact when you discussed in our next lecture regarding the application of the reaction mechanisms. Then moving further, let us understand how you want to illustrate, how you want to see or view this chain initiation or chain propagation mechanisms. So, if you look at global reactions which you normally see, A2 plus B2 in general gives 2AB, it is a hypothetical reactions, and for these 2AB formations there may be series of a sequence of events. So, first we may have the A2 with some, by colliding with some molecules, it can form A plus M, and this A again can, when it sees B2, it can form AB, and this B when it says again A2, it can form AB plus A. So, through this process AB gets concentration gets built up, and when the chain terminates, finally what remains is AB. So, all A plus B plus M should be merged with AB, and this M vanishes, and through this process we get different rate coefficients, and we need to find out what are the relation among them, and those relations can be built up with the knowledge of the equilibrium products. Then another important aspect that we are going to discuss is the chemical time scale. So, we all aware of the time scales. Time scales is normally represented either in hour, meter, second, year, depending on the nature of the event. But in the chemistry, we see the time scales in a very short duration phenomena, or it is a very small event. So, how do you view this? Now, we have unimolecular, bimolecular, termomolecular reactions, and all of them will have a different time scales. And if at all you need to define a time scale, how do you quantify this? So, this is the basic philosophy for determining the chemical time scales in a combustion process. The analysis of combustion process requires precise knowledge of chemical times relative to convecting mixing time of importance. So, what it means is that, so when the combustion phenomena normally takes place, either it is has to be done through a pre-mixed mode or diffusion mode, and the flame gets established and it keeps on propagating, and to keep it in a sustained mode, we need to find out that fuel and air mixes properly, and this mixing process has some finite time. At the same time, during the mixing process, it may so happen that, but your chemical time scale, So, during the mixing process and chemical time scales, they should be at par. That means, if your chemical time scale is in milliseconds, your mixing time should be in the similar durations, so that we can ensure that maximum fuel is burnt. So, the knowledge of precise knowledge of chemical time scale is very vital. So, for that purpose we need to find the expression for characteristics time scale to be formulated for the elementary reactions, that is unimolecular, bimolecular, termomolecular reactions. So, let us start with an assumption that we are looking at a unimolecular reactions. So, when I say unimolecular reactions, element A gives the products with its apparent molecular rate coefficient K apparent. So, we can find an expression that how the rate of the concentration of A changes, because its negative sign says that concentration drops with time, and that is equal to K apparent into concentration of A. Now, this particular equation can be integrated to find out A into T, concentration of A into T is equal to initial concentration of A, that is at the beginning, and it is e to the power or exponential e to the power minus K apparent T into T. Now, here we introduce the term what is called as chemical time scale, or many times we call as characteristics chemical time, and it is the time required for concentration of A to fall from its initial value, and this initial value means A0 to have value equal to 1.8 times of its initial value. So, concentration of A when we multiply by this, so we will have initial concentration which is A0 is equal to 1 by E. So, by this definition, why it is called 1 by E? Because with this number this logarithmic expression gets simplified. Then from this, by putting this expression here, we can write exponential of minus K apparent into, instead of T we can replace with tau chemical, it is 1 by E. So, from this we can find for a unimolecular system chemical time scale is equal to 1 by K apparent. This is what we call as a characteristics time scale. Now, in the same context, the expressions for chemical time scales for bimolecular and termomolecular reactions can be obtained. So, in a bimolecular reactions with the same philosophy, we can have expressions tau chemical, because in a bimolecular reactions we require two species, concentration of A, concentration of B, it gives C and D, and we need to find out the chemical time scale for A. So, first term should be A. Now, when I write this chemical time scale, this expression refers to for the chemical time or characteristic time scale for species A. For this species A, we need to find what is the initial concentration A0. And similarly, if the reaction is termomolecular, then we also need to find out the first term, that is species A, and this refers to this characteristic time scale for the species A. So, for a simple compressed simple system at constant temperature, the third body concentration AB is constant. So, the rate of expression is mathematically identical for bimolecular systems. So, basically bimolecular and trimolecular they remain same. What remains the final expressions is that when the concentration of B much greater than A0, this chemical time scale refers to a very simple expressions for unimolecular reaction and for termomolecular reactions. Now, if you look at these two particular reactions and if you compare the original reactions A plus B is equal to C plus D and A plus B plus M is equal to C plus N, then both chemical time scale characteristic time scale for bimolecular and termomolecular reactions appears to be same, only is just a difference in the concentration. Now, next topic of discussion that we are going to explain is about partial equilibrium. Many times what happens, complete equilibrium analysis may not be feasible in certain situations. To why? Because some reactions are very fast and some reactions are slow. Many times forward reactions are fast, reverse reactions are slow. That is because, for example, when you say intermolecular reactions, they are basically chain terminating mechanisms. So, that is the stopping time. So, these whatever species have formed, they try to recombine and settle down. So, when this happens, it is almost the analysis may be difficult if you wait till the complete equilibrium situations. What has been a probable or a feasible approach is to consider partial equilibrium. So, for this consideration, we say the fast and slow reactions has to happen such a way that and they can happen in forward and reverse fashion. Now, out of all the reactions in a given system, one can pair out some particular reactions that gives similar products or same products. For example, in this situation, when A reacts with B2, it gives AB and vice versa. B can react with A2, it can give AB plus A, and both the reactions can form the species AB, and in both the cases we can pair them out. So, that can be considered as a one single pair. While doing so, it is logical to assume that rate of forward reaction and rate of reverse reaction are known, and you can express them in terms of their equilibrium constants. And from this, it is possible to evaluate the concentration of the actual reaction which is occurring. So, actual reaction which is this is A plus AB plus M is equal to A2B plus M. So, A2B is the real need of our requirement, for which we need to find out. So, from this, to get this reaction, we need information about the concentration of A, concentration of AB, concentration of M. So, these individual concentrations can be formulated by assuming through what we call as a pair mechanism, and they fall under the criteria of partial equilibrium approximations. So, by treating fast reactions as if they were equilibrated, this simplifies the chemical kinetics by eliminating the need to write the rate reactions for radical species. What it means is that when the elementary reactions get started or chain gets built up, chain initiation has been done, branching has been done, and through this that radical has been formed. So, we need to make a partial equilibrium assumptions to find out the equilibrium concentration for the final species, and this process avoids the need to write the rate equations for individual radical species. And here I need to try to emphasize there are some reactions which are paired, and they are called as shuffle reactions, and because these radicals, the species are shuffle among those reactions between the reactants and products, and this helps us to find out which is a faster reaction. Faster reactions are normally bimolecular reactions in the forward or reverse fashion, and slow reactions may be intermolecular reactions because they are in the phase of recombination or rearrangement, or the reaction, those reactions settle down soon and they are very slow. Okay. With this, we come to the end of the lecture, and based on our understanding, we will try to solve a numerical problem. So, this numerical problem is all about finding out the characteristic time scale for a certain reaction. So, we have already defined the nature of time scales for unimolecular, bimolecular and intermolecular reactions. What has been given is that one particular reactions, that is CH4, reacts with a radical OH and it gives CH3 plus H2O. So, this is one particular elementary, or I mean you can say chain initiation or chain branching reaction, and for which the rate coefficients are defined in terms of centimeter cube per gram mole and seconds, and it is a function of temperature 10 to the power 8 into T to the power 1.6 exponential minus 1570 by T. and the reaction is happening at 1 atmosphere, but 1344 Kelvin, and this reaction is a bimolecular reaction. Because we have two species CH4 and OH, and what has been asked for characteristics time scale for OH. So, basically when we are finding out OH characteristic time scale for OH, then we have to rewrite the equation keeping OH first. So, we will write this expression OH plus CH4 gives rise to CH3 plus H2O. So, this refers to the fact A plus B gives rise to C plus D, and for this in a generic term we are looking at the characteristics time scale for A, and when you do that, the basic definition or says tau chemical or characteristics time scale is ln E plus 1 minus E into concentration of A0, that is initial concentration, concentration of B0, and this divided by concentration of B0 minus concentration of A0 into K. K is rate coefficient for bimolecular reaction when the reaction happens in these directions, and in our case this K is given as this expression. K is equal to 10 to the power 8 T to the power 1.6 exponential minus 1570 by T. Now, putting T is equal to 13544 Kelvin and all the parameters are known, then we can find out K, and its K has unit centimeter cube per gram mole second, and this number is 3.15 into 10 to the power 12 centimeter cube per gram mole second. Okay. But what other thing we require? We require initial concentration A0 and B0. Now, let us see in our case what is A. So, our case A stands for OH, B stands for CH4, and we need to find out their concentrations. So, OH concentration we can find out, and this concentration we have to find out because we have given with the molar fractions. So, molar fraction needs to be converted to molar concentration. And for this we require the expression or information about the pressure and temperatures. So, if I can write that conversion, then I can write X OH concentration is molar fraction of X CH4 pressure into R bar T, and pressure is X CH4 is given, X CH4 is 2.012 into 10 to the power minus 4, pressure is 1 atmosphere, that is 101,325 Newton per meter square, R bar is 8314 joule per kg mole Kelvin. So, you say 8314 into temperature is 1344. So, we can get concentration of OH as 1.648 into 10 to the power minus 9 gram mole per centimeter cube, and again we require concentration of CH4. CH4 concentration can be written in a similar fashion as X, here it should be OH and here it should be. So, OH concentration is 1.818. When I put OH concentration is this. So, it is X CH4 into P by R bar T, and this X CH4 is 2.012 into 10 to the power minus 4, P is 101325 divided by 8314 into 1344. So, it will give OH concentration as CH4 concentration as 1.824 into 10 to the power minus 9 or gram mole per centimeter cube. So, it is OH concentration, so it is gram mole per centimeter cube. Then we have B0, A0 and all these terms. So, we can find out T chemical time scale as ln. First term is E is 2.718 plus 1 minus E is 2.718, 1 minus E means minus 1.718. Concentration of A0, A0 is our OH. So, it is 1.648 into 10 to the power minus 9 divided by OH is 1.824 into 10 to the power minus 9. Entire number divided by concentration of B0, B is CH4, that is 1.824 into 10 to the power minus 9 minus 1.648 into 10 to the power minus 9 whole bracket, we have K bimolecular reaction. This is this number into 3.15 into 10 to the power 12. So, after simplifying this, the tau chemical or chemical time scale for OH, OH is your this term is equal to 0.28 millisecond. So, this gives the information that in a bimolecular chemical reactions, the order of characteristics time scale is about milliseconds, and in this case the time scale for OH species is 0.28 millisecond. With this I conclude. Thank you for your attention.